All we're doing is going back over and applying ideas that we've already talked about multiple times. Identify the type of each function represented in each table. And one of the things we want to look for is differences. So if I look for my first differences here. Oh, you know what? Maybe that's the problem. Let me try this. Yep, just like an 8th grader. Doesn't do what you tell it, smack it around.
And then get fired.
No, this is a parent. All right, here we go. Ready?
Then get arrested for domestic violence.
Go ahead, give the kid on his own. He'll find out it's a whole lot better at home. Okay. Now, in most homes, there are some that are really sick of the method, but a smack upside the head when a kid does something really bad is for their own good. Okay. Anybody here ever get smacked upside the head for doing something really stupid around the house?
I've been spanked.
Yeah, me too.
Spanked. When I say smack upside the head, it's a New York Jack kid.
I do that to people all the time.
Yeah.
I'm a princess.
I did that to Anthony, and he was so mad.
All right. When Gibbs does it on TV, if Gibbs can do it, anybody should be able
Because
to
he's
do it.
just like,
That's right. Just come on. You know better than that. What are you thinking? Right? All right. So we take a look at table A, and what are we going up by there? 2. This is what we call the first difference. It's the first time we subtract, and when the first difference goes up by a common amount, what kind of sequence is it?
linear.
Well, that's what kind of function it is. Well,
Arithmetic.
arithmetic sequence, linear function. Very good. As I take a look at this one, as I look for my first differences, I notice that there's not going up by the common amount. So one of the other tests I could do is I can, instead of looking for, good job at night, instead of looking for a common difference, I can look for a common ratio. And if I do my division, every time I come up with 1.5. So this is an example of a what kind of sequence?
Exponential.
That's the type of function. What type of
A
sequence? Geometric sequence. Very good. All right, and this guy, here's where second differences can come in and be a big help. If I look for first differences, I come up with 12 minus that's 9, 15, 21, 27. Bones. And then I could say to myself, well, look, do you notice the pattern of 6 here?
Yeah.
That's worth noticing. So that'll be what we call a second difference. All right? When a second difference is constant, it's a quadratic. Constant, not constants. When the second difference, that's why we call you bones. When the second difference is a constant number, whatever that constant number is, it's going to be a quadratic. So this is not a linear, or I should say, I'm sorry, it is not an arithmetic sequence, it's not a geometric sequence. It is in fact, in terms of functions, a quadratic function. Now, how else could I know this? There's another way to do it. I happen to notice that 1 squared is 1 times 3 is 3, 2 squared is 4 times 3 is 12, 3 squared is 9 times 3 is 27. So I noticed that the equation for this is y equals 3x squared. Okay? So that would get the last one going. We could go back to something we did a long time ago, which I would prefer not to go there right now because we just don't have the time for it. Y equals a times x minus h squared plus k. If I go back one more to 0, look at this. It's 27 to 21 to 15 to 9. We're going down by 6s. I'm sorry. We're going down by 6s from 9, which takes me, 9 minus 6 brings me down to,
-3.
no, that's not what I was going to try to say.
It's down by 3, so it's 0, 0.
Right, exactly. Now,
So it doesn't move over.
well, yeah, what happens is, the bottom line is that k becomes 0, and then you got to plug in the x and the y, and you got to work it out and figure out what the, you got to do 2 of them, right? And then when you do the 2 equations, then you can simultaneously solve for the values and so on. I don't really want to go there right now. We did that a few weeks ago. Okay, as far as this one goes, this equation is going to be y equals, now the initial or starting amount is 6, the common ratio is 1.5, and we talked the other day about how this would be x minus 1, because we need this to be to the 0 overall for the first term. 1 minus 1 is 0, 1.5 to the 0 is 1, 6 times 1 is 6. So the correct equation is y equals 6 times 1.5 to the x minus 1. And we spent a lot of time the other day talking about why that exponent is x minus 1 and not just x. Okay?
Where'd you get the 1.5?
The common ratio. 9 divided by 6, 13.5 divided by 9 will always come out to 1.5. Okay? And likewise, as this uses a common ratio, what? The x minus 1. as we look here, I see that it's gonna be y equals 2x, because I'm going up, and I'm going up by 2, so 0 would pair up with 3, so y equals 2x plus 3 is the correct function for there. Now, what do you do if you're staring at the table and you're saying to yourself, man, oh man, I'm not sure. Is it quadratic? Is it exponential? Is it linear? What are we looking at here? Well, we can always go to plan B. You can actually graph the points and get an idea of the shape of a particular figure. And we can actually take and combine those ideas with some of the first and second difference ideas, and so on and so forth. So I'm going to need a little bit of help here. I sense a lack of concentration on the part of some right now. Thank you. It's wonderful when kids police themselves. Now, since Melissa, you really do want to talk so much right now, I'm going to ask for your help. Can you tell me the coordinates for table A?
1, 5,
Good.
2, 7,
Oh, hold on, I did that. Yep.
3, 9,
Yep.
4, 11, and 5, 14.
All right, good. Is it pretty obvious I'm going to make a straight line?
Linear.
Right? Yeah, so linear was our answer, and that confirms that linear was the correct one for that. All right, so I'll do this one too, blah, 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 whatever. Yeah. Again, I'm only sketching here so I can get a clue what it's like. Let's go with CJ. Table B. What are the coordinates? You just have to read it.
Oh, 1, 6.
One. What's the highest level?
30.37.
All right, so I'm going to do each one is equal to 3. Okay, so we got 1, 6. What's next?
2, 9.
Mm-hmm.
3, 13.5.
Mm-hmm.
4, 20.25.
Okay.
And 5, 30.375.
Can you see that we have what looks to me like an exponential bend there? Right? Okay. So that confirms exponential. Now let's go with the next one, which we feel is most likely to be quadratic. Okay. All right, for this one, let's go with Anthony Randall. Go ahead.
1, 3.
All right, what's the highest number, like 75? All right,
yes,
I'll do them
75.
3s each. 1, 3, what's next?
2, 12.
Okay, next.
27. 4, 48. And 5, 75.
All right, that's up there somewhere. And what we have here is you can notice that I'm going to come down, the path goes to 0, and then I get a matching one on the other side to be quadratic. The reason I could tell the green one is going to be quadratic and not exponential like the blue one was that whole second difference is a constant. They all came out to be 6 on the second difference. That's what tells me that it has to be quadratic. Okay, very good. Let's turn the page. A very typical type of Regents question that you would get with these questions is you would get 4 tables, and they would say, which of these 4 tables is exponential? And they'd probably do it different, like, Johnny put his money in the bank at 3% interest over, whatever, 30 years. Which of the following graphs could represent this? Or they would actually write out the table and ask you which of the graphs it could be, or they'll just show you the graphs, and they'll say, which of these tables is exponential, which of these graphs is exponential, et cetera. So you have to be able to recognize each, as well as to actually draw them on your calculator. Enrique is a biologist who's been monitoring the population of a rare fish in Lake Placid. Now, I happen to think that this is pretty humorous, because didn't they have that movie called Lake Placid with that, like, vicious animal fish in there? He has tracked the population for 5 years and has come up with the following estimates. Okay. Oh, you know, in the other class I did this slightly differently. I didn't realize there was a column in the middle for years since 2002. So I can actually do it without the break. All right. I'm going to need someone again to read those numbers off to me. So let's graph it and let's follow. But when I do this, this is going to be your 0. And then this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what is the initial population? Is it like 100? 1,000. All right, so I'm going to do 100, 200, 300, 400, 500, 600, 700, 800, 900, and 1,000. Okay, so we're going to look for general trends here. It doesn't have to be absolutely perfect. In year 0, there's 1,000 fish, right? All right, what is it in year 1?
899,
Which is, for all practical purposes, 900. What about year 2?
796,
Almost 800. There we go. Year 3?
691,
Go ahead. Year 4?
584,
Okay.
and that's the end of the graph.
Okay, so it's pretty much 100 fish a year it's going down by. And if I draw my graph, I end up just shy of 10 years. So it looks to me like on year 10, we run out of fish again. Okay? All right, everybody, that was the last question of the day. So now you can just proceed forward and get that homework done. Hasta la vista, vaya con Dios, toodaloo, ta-ta. Arrivederci, smile a lot. See you later, Hammer. Arrivederci, adios, amigos y amigas. We got Karusharus, Codefish, or Kadafis. How did I say that right? Kadafis? Kadafis. Like Daffy Duck. Okay, Kadafis. Good, we're cool.
Next, or should I just go down and find the janitor?
Hmm?
Should I find the janitor on my front locker?
That's your next teacher.
Mm.